Alrighty. Lab yesterday. Did you learn a few things in lab?
Yes.
Did it help you with the homework? No.
No. There was one problem that had like 3 unknowns in it. It took me a good solid hour and a half to try to figure out how to solve it.
You can always contact me. You know,
I got it eventually.
Yeah, but an hour and a half is a long time to work on a problem. My goal is not for people to spend that kind of time on a single problem. But the goal of the lab, of course, was for you to be able to solve those circuit problems, to apply the rules that I told you about in class. And then your homework is like 4 out of 5 problems are doing the same thing again and again to make sure you have it down. Why again and again? Because it's not something simple that you do it once and you have it. So make sure you know the rules. You definitely will have to use that on the test. I always have solving a circuit on the test. So there should be no confusion like, oh no, that came up. Just to make sure that it is clear, I was going to send an email, but there were 2 groups that did not have time to measure the currents on the second circuit and only measured the voltages. And so what you guys need to do if you're in one of those groups is you have, the measured R1 and you have your values. And then you have current and put calculated here. And then just take the value that you had, for the voltage divided by the resistance value. So for those that didn't have time to measure current for the second circuit, you're just going to calculate this as, you don't need to show the calculation, but I'm showing that because that's what you're going to do. But make sure you indicate there that it's calculated, so when the grader goes through, the grader understands there's no uncertainty here because it's calculated based on the measurements for voltage. Yeah.
So we don't have to do anything with the program? Yeah, it's in the computer then?
No, you still have to do that because you're going to compare the currents that you calculate here with the currents you get from your analysis.
Okay, so you would just do it on the calculator then? Is that what you want? Or?
No. What I'm saying is you're calculating these currents here so that you can compare those with the ones that you calculate with your circuit analysis. So you're calculating these based on your measured voltages. So we're considering these. For everyone else, they were measured currents. For the 2 groups that didn't have time to measure it, they're going to calculate the current based on the measured voltage and then compare that to what the theoretical current should have been. Okay, let's move into a simple question relevant to yesterday. In this diagram, which side of that resistor is the positive side and which side is the negative side? Okay, so we have A or B. Which one's positive? B. I tried to emphasize that yesterday because when you're going through, one group, it made me so sad. They had one of the currents backward, and instead of keeping it that way, when they measured and saw that it was backward, they changed their definition of the current direction. You can't do that with the homework. The homework intentionally has it so some of the currents are backwards, so you get negative current values. So you see, not a problem. It's just a negative current that direction, which means it's actually going the other direction. So it's important that you have that down so when you're going through a loop that you can calculate, voltage rises have plus signs, voltage drops have minus signs. One last thing, Dr. Seth McNeil came in during lab and he was talking to some students about how to solve the circuits. What we have learned here is the fundamentals for solving circuits. So we're doing it in, shall we say, the simplest manner, but not the easiest manner. This is the manner that takes the smallest amount of understanding. The method that he was showing the students, which is called nodal analysis, is taking the ideas that we've learned and redefining the circuit to make it so you can solve it easier. So we have nodal analysis and mesh analysis that are two different ways of using the same rules to solve the circuits. It's more complex but easier to do. So like I just got to the point where I solved all circuits with mesh analysis at one point in my life. But I'm teaching you the basics, and that's as far as we go. So that's why your method is not the same as the way he was saying, oh, just do this, this, this. So just so you know, what we're doing is right. It's just the basic way of doing it. Capacitors. Only a few things on capacitors, and then we're going to get to magnets. And I should have had all of my cool little magnet demos out, but I don't. Capacitors. I guess I haven't given you yet the worksheets, have I? I do have 2 of them done now. I'll post them after class. One of the things I have on there is what the purpose of a capacitor is. What is the purpose of a capacitor? Okay, storing energy in the form of, and you can either say a charge separation or an electric field. Either one is perfectly accurate, right? So it's not like one is preferred. It just depends on the situation which one we're going to talk about. So right now I'm going to talk about storing energy in the form of a charge separation. And so this is a way capacitors are used in electric circuits. If I have a switch here, and initially the switch is open, so that means there's no circuit. What do you have to have for a circuit? What's the definition of a circuit?
It has to connect. Be in a loop.
It has to be in a loop. And so if the switch is open, the loop is broken. That's why it's no circuit. So if there's no circuit, how much current flows? That's a definitional question.
0.
0. No current flows because you don't have a circuit for it to go around. So if that switch is open, there's no current flowing. When the switch is closed, then I have a complete circuit, then current can start to flow. So let's suppose I start with that capacitor completely discharged. The charge on the top and the bottom are both 0. So plus Q and minus Q are both 0. The instant I close that switch, current's going to start to flow. Now what's the voltage on the capacitor if the charge is 0? Remember that?
0.
0, because the equation is Q is equal to VC. So if Q is 0, V is 0. So initially there's no voltage across that capacitor. When I close the switch, charge doesn't magically appear on the capacitor. It's going to start flowing to the capacitor, but it doesn't magically appear. So the instant I close that switch, it's still going to have 0 charge for that instant. I'd like the need for that one.
I don't know. Someone said, I've already had so many pastries. Please take these. So I decided to help them out.
You're a good man. Yeah, I like what he's saying. You guys, I'm sure have not seen Fast Times at Ridgemont High, but a student orders a pizza in the middle of class. Delivery guy comes to deliver the pizza to the class. Teacher gets upset. Student says, yeah, teacher. Okay, I've started, I can't stop. The teacher says, this class time is my time. And you can't be eating on my time. And Justin Coley philosophizes, well, you have to be here, I have to be here. So does that make it our time? What's wrong with having a little feast on our time? And then the teacher, and this is where Ryan comes in. Teacher says, you're right. We should have a feast on our time. Here, everybody come take a piece of pizza. And he gives away always pizza too. Yeah, okay, so that was really good. You got me way off topic just by having those sitting there. So back to this. You're going to have, initially the charge was 0. When you flip the switch, the charge on the capacitor is going to remain 0, which means the voltage is going to remain 0. So as soon as I flip that switch, the voltage on the capacitor is still 0. So if you're at, let's say this is 10 volts here. If that's 10 volts and you have 0 volts here, then the voltage here is the same as the voltage here, and you have 10 volts across the resistor. And so you're going to have current flow because you have that 10 volts across the resistor. And so you can use Ohm's law, I is equal to V over R, and you're going to have a bunch of current flowing. But as soon as current flows, what's that going to do to the capacitor? If I have current flowing, what's happening to this side of the capacitor? Okay, it's building up negative charge. And the other side is going to be building up positive charge. Because nothing in the circuit, including a battery, is supplying charge or taking away charge. The amount of charge that is added to one side is removed from the other. So the two sides are going to have the same charge, one positive, one negative. But as it adds charge, then the voltage is going to increase. And if the voltage on the capacitor increases, the voltage on the resistor decreases. If the voltage on the resistor decreases, what happens to the current? Decreases. Yeah, because I is equal to V over R. So the voltage difference on the resistor decreases, then the current decreases. So you're going to start out with a maximum current, and then it's going to drop off with time as the voltage on the capacitor rises with time. Until after a very long amount of time, you'll have all of the voltage here is on here, and then the voltage across the resistor is 0, which means no current flows. So we call this charging the capacitor. The actual equation for charging the capacitor is this. Now, people in the physics with calculus class, we will be deriving this probably next week. But the voltage across the capacitor is the peak voltage, using the terminology of this circuit, I'll put the EMF, times 1 minus e to the minus t over RC. So it has an exponential term here. And notice e to the 0 is 1. So at time equals 0, it's going to be 1 minus 1 in parentheses, 0 voltage. And as time increases, it goes up as shown in this curve. So it's going to charge quickly initially because the current is high. But then as the voltage on the capacitor increases, the rate of charging decreases, hence the curve. Important things to know, this RC, we call it the RC time constant for a very obvious reason. It's time divided by RC, so it has to have units of time. And the bigger RC is, the longer time it's going to take to charge. So you can adjust the charging time by adjusting the values of R and C. So if I have a big RC, slow charge. A small RC, quick charge. Where would something like this be useful? Well, let's say you have a camera flash. Your camera flash has a circuit actually want to put okay, that's what I want. Genius. So your camera flash has a circuit something like this. Here's the flash. The flash is going to dissipate a lot of energy. And so you need to store a lot of energy. And that energy is coming from a battery. Actually, it's usually a cell, like a 1.2 volt cell. So let me make it a cell. 1.2 volts. First thing we want to do is charge this capacitor. Still got one thing missing. First thing I want to do is charge the capacitor up. And so I'm going to I have my resistor there. That's my charging resistor. And of course, my flash is my discharge resistor. When I close the switch on the left side, that will charge. So this is the charging configuration. And I'm going to have current flow from my cell into the battery. Now the little cells, 1.2 volt cell, it can't provide that much current. So no matter what the RC is, it's going to be a relatively slow charge just because it can't produce a lot of current. And so if you want to take a picture with a flash, you turn on the charge and it takes a few seconds for it to charge up. Then when you're ready to take a picture, you're going to flip the other switch. And so you have the flash here. And when you do that, it's going to discharge through that resistor. Now we want to store a lot of energy. What's the equation for the energy stored? What's the equation for the energy stored in a capacitor? Not remembering? It's 1/2 capacitance times voltage squared. Well, that voltage squared is only 1.44, right? 1.2 squared is 1.44. So the voltage squared part is pretty small. So what do I have to do with the C part to have a reasonable amount of energy stored? I need to increase it. I need to have a pretty large capacitance to store a fair amount of energy. But then when I discharge it, it needs to discharge quickly. So what does the resistance of the flash have to be for it to discharge quickly?
Very low.
Very low. So we have a low resistance in the flash so that we can dump all of that energy very quickly. If it was a high resistance, it wouldn't work. It needs to be a low resistance to dump the energy quickly to make a big flash of light. So this is an example where the capacitor is used to store energy. The battery has a lot of energy it can supply, but at a slow rate. Transfer it to the capacitor stores the energy, and then it can deliver it at a high rate. Now that brings us to things like this. I have my phone, and I have to charge this stinking phone like every single night. I could do things the smart way, right? Like I said in lab, I can stick it in the microwave. You've seen that on YouTube.
It works.
Yeah, it works. Yeah, in case anyone takes that seriously at all, no, it doesn't work. Okay, so it takes like an hour or 2 hours, depending on your phone, to charge the phone. And people get really frustrated with that, right? Well, one idea people have is let's replace the batteries in our phones. Batteries are providing energy that they have stored in a chemical reaction. Let's replace those with capacitors. Let's make a supercapacitor that will store the same amount of energy, but with the capacitor, you can charge it really quickly. You just have to have a really small resistance for the input side, and you can charge it quickly because you have that RC time constant. Sounds great, right? Except for there's the downside. What happens when a battery goes bad in a phone? Let's say that you bought a Samsung, what was it, Galaxy 7? Or I forgot which one it was.
S9?
Well,
Oh,
no.
True. The one that explodes.
So the one where they built them and they didn't put enough space for
So it explodes.
the battery to expand. And they started fires and did bad things. Well, that was with the battery, which doesn't release the energy quickly compared to a capacitor. If you had a capacitor and you had a similar problem, it would really explode. It would be a much more violent thing because it would deliver the energy much more quickly.
So it exploded because it couldn't expand?
That's my understanding. In the end, it was, they were initially blaming the batteries themselves, but my understanding is eventually what they determined was they didn't have enough space inside for, when things heat, they expand. We've learned that. And so when the battery is being charged, especially, it gets hot, or when you discharge it quickly, it gets hot and it expands. There wasn't room for that, and that's what caused the compromise that resulted in all the fires.
How much does a capacitor expand?
I don't know about capacitor expansion. What I know is it would deliver the energy really quickly if something happened bad. And so, you take your iPhone, you drop it, and it explodes. It's not really the best plan. So I don't think we're ever going to have supercapacitors in our iPhones. But it is something that could be used as a fast charging storage device, much faster than trying to move chemicals in a chemical reaction cell. Okay, I spent way too much time. I did not intend to spend that much time at all on capacitors. The discharge is basically the same calculation as we did. It's just you start without a battery and you just have this discharging, so the voltage across the resistor is equal to the voltage of the capacitor. And so the current is proportional to the voltage of the capacitor. And in that case, the discharge is, I should put D for discharge, is equal to V max E to the minus T over RC. So once again, you can adjust how quickly it will discharge by adjusting R, just like you could adjust how quickly it will charge by adjusting the R. This is used in timing circuits as a nice example. You have a circuit that charges something up, and when it gets to this voltage, it allows it to discharge through a capacitor, and when it gets to this voltage, it starts charging again. And so because of those RC time constants, you can set a nice, easy frequency. And so if you've ever used something with a 555 timer, I'm guessing that's none of you, that's what you do, is you would just adjust the resistance and capacitance using these ideas, and it just has discriminators for when this drops below this voltage, it's going to start charging. When this goes above this voltage, it starts discharging. We'll get to AC circuits and talk about more uses of them later. Here's a picture showing a timer circuit. This timer circuit is actually really simple. It uses a gas discharge bulb, I believe. I think it's gas discharge, so that you have no current flowing in the bulb until you get to a certain voltage, and then it will have current flow until it drops to a certain voltage. And so that gives you an oscillating, not a nice sinusoidal oscillation, but oscillating current. Okay, I think I have electrical safety. Nope, I don't have electrical safety here. Let's talk about electrical safety before we move on to magnetism. Is electricity safe in general? I'm going to go with yes. Can electricity kill you? Most absolutely. So basic things to know about electricity and safety. Our bodies basically run on electricity. If you have something that's like a milliamp going across your skin, you'll feel it. Maybe. A little stronger, you'll definitely feel it. You get up to like 10 milliamps, and it'll start making your muscles contract. So like, you go to the chiropractor, and he puts those little electrodes on your back, turns up the voltage. It's an alternating current. And those alternating currents are making currents go across the muscles, making them contract. And so I used to have them turn it way up because, man's got a decent pain. And you get to the point where you try to relax and your shoulders go like this. I have to do it on my shoulder. Shoulders go like this. And then I was able to force it to relax. And then as soon as I would stop concentrating, it'd make them tighten up again. Because the muscles are running on electricity, and when the current gets high enough, it forces the muscles to contract. That's what makes them contract. So if you get up to like 10 milliamps of current across a muscle, it will start involuntarily contracting, right? It's doing what your brain usually tells it to do because of that external stimulus. Now, I think this would be the great way for us to get in shape. In fact, they used to, I don't know if they still do, they used to advertise like on late night TV. You buy these little pads that you put on your stomach. You sit and watch TV, and it's having alternating current going across your stomach to tighten up those abs. They still sell those things?
Russian Eastern.
Russian Eastern, okay. It seems like a great idea. I want to just go to the gym, hook these up, hook the electrodes up right, and have somebody just program a computer. So I go lie down on the bar, and it makes my hands clamp up, and then it makes me push and pull and push and pull and get my workout without me having to have the mental fortitude to do the lifting myself. Genius, right? It's, for the most part possible. And there's a lot of research in trying to use things to control muscles, so you can like have somebody who's paralyzed and have something that is taking external cues and using those to put voltages on muscles to make them contract, so a person can do things when their nerves aren't doing the communication to tell them to do it. Because we run electricity. Okay, so keep it going. Safety. Yeah.
So is that why when you grab onto something that's electrified, you can't let go?
That's exactly right. Yes. The point of the lecture is the safety. Let's say that you have more than 10 milliamps. Your muscles contract. So the first thing she said, if you have an electrical wire, you're like, well, golly, I wonder if that thing's really electrified or not. You touch it. If you touch it like, okay. If you come out and say, well, let's check it, and you go like this, if it has a high enough voltage that the current through your body is over 10 milliamps, it's probably going to make you go like this. And then what happens? You can't let go because your muscle is now contracted. And so you sit there going, that's not good. We agree? Now, what if that 10 milliamps or more is going across your chest? That brings up a real safety issue. Because we do this thing, I like to breathe. I do it all the time. And the way we breathe is first, we relax. And when we relax, we expand a little here. And atmospheric pressure forces air into our lungs. Right? You cannot breathe without atmospheric pressure or some external pressure pushing air in. And then we tighten up these intercostal muscles, pull our ribs together, push the air out of our lungs. We also pull the diaphragm, singing, sing with your diaphragm. So we push the air out of our lungs. Well, if you've got that current going across your chest, what happens is you go, you suffocate because you can't breathe. Because you just pushed everything out and you can't let anything back in. So one of the first risks with electricity is suffocation, which is pretty much not the way you want to go, right? You're shaking about and you can't breathe. You don't want that. So that's the first real deadly thing. Second deadly thing is dealing with the heart. If you have a current that goes across the heart and it's more than, say, 50 to 70 milliamps, then it can cause currents to go wrong in the heart. Or you can cause the heart to seize if it's too much. And so, if you have a consistent current going across the heart, you're going to make bad things happen. And even one jolt across the heart can either make the currents in the heart go in the wrong patterns, where you get fibrillations. Remember I said my EMT teacher said, it's quivering like jello, but it's not pushing any blood because it's not working in a coordinated effort. Or if you have even more current, you'll stop the heart. So if you get up to 1 amp across the heart, it's safer. It's safer because it's likely to just stop your heart. I say just stop your heart. If you stop your heart, there's a good chance it will start up again normally. Good chance. It's also a chance it'll never start up again. So that's another way that electricity can be damaging if you have more than 50 to 70 milliamps going across the heart. And then the final way, like Farmer John's Franks, you can have enough current. A family friend, he was out changing sprinkler pipe, and he had rodents in the pipe, and so he went like this to get the rodents out of the pipe. But there was a high power line up there, and his sprinkler pipe hit the high power line. And I, of course, did not see him after this, but they said that you could see the burn marks in his hands where the current went in, and you could see the burns on his feet where the current went out and into the ground. And if you were to section him, you would have seen burns through his body. Right? That's very bad. So there's a number of ways electricity can damage you. In all cases, it's the current that matters. But of course, our bodies have resistance. And so there's a relationship between current and voltage. So if it's DC, direct current, then the calculations are pretty simple. You're just going to take the voltage divided by the resistance across your body, and that gives you what the current's going to be. The resistance of your body comes primarily at your skin. If you cut inside your body, the resistance is very, very low. But your skin has a resistance that's in the order of tens to hundreds of kiloohms, which limits then how much current you're going to have. When you go a high enough voltage, the current will be high enough to be dangerous. Hence the signs that say, warning high voltage. And all the smart Alex say, it's not the voltage that kills you, it's the current. Yes, but if it's high voltage, it's going to be able to put a large current through you. That's why it has warning high voltage. So voltage is an important factor. Now, if you have alternating current, things change a little bit, so we won't deal with that. Ohm's law still applies in alternating current, as we'll learn soon, but it's a little bit different in the way the body responds. Really high frequencies, it won't penetrate your body type of thing. Okay, so looking at this circuit, now that I've talked about electrical safety, let's say you have a high voltage circuit here that's like, 10 kilovolts. That's high voltage. And then it's going to a capacitor so that it stores the energy. The reason you use a circuit like this is so you have a consistent voltage. If it was just the power supply, you'd have the voltage drop more quickly as you use the energy. Using the energy in pulses, the capacitor will help to keep it more constant. If you turn off the power supply or if you break this wire, is it then safe to touch the resistor? No, why not? Because you're still storing energy on this capacitor. And so you need to wait until that capacitor is drained. And sometimes there is no load on that capacitor unless a certain switch is flipped. And so it can sit there and hold a high voltage for a very long time. Hence, when I was working, I used to have a projection, or not, a rear projection TV. And things went wrong, so I had to work on the circuit board. And, there's a little place that you're supposed to put in a stick, and it has a stick. You put it in there, and it discharges the capacitors. That way, you don't have to worry about being electrocuted. It's a good thing. Funny story. When I was teaching at PUC, I was actually driving through San Francisco when this happened. All of a sudden, all the lights went out. Stoplights are out and everything. So, of course, driving San Francisco without stoplights is a hazard. We get out of there, go home, like, what in the world happened? What had happened is they had been doing some work on the BART-Berry rapid transit system. And of course, they were doing electrical work. And to make sure people aren't electrocuted, they turn off the power, and then they have these big rods that ground between the hot side and the ground side, so that if somebody accidentally were to turn on the electricity, the power would go through those rods and not through people working. Right, that's a good safety thing. And so after the work is done, they have to go through and take out all of those rods before they turn the power on. Well, this is union employees at their best. They have a check sheet. Did you remove this? Yes. Did you remove this? Yes. Did you remove this? Yes. They're all checked. They turned on the power. But they hadn't removed like 11 of these grounding rods. And so the electricity went through those grounding rods, a direct short basically coming from the power plant to those rods. And so with that direct short, it destroyed the power plant. What actually happened was current, voltage over resistance. If you're dividing by roughly 0 for resistance, that current gets really big. And the demand on the sudden demand at the power station was so large that it caused the generator shaft to shear. And so it broke the generator at the power plant, and power went out. Just talking about the safety issues here. I know it's a little more than we needed for safety, but good story. Magnetism. What's in this ultra cool picture here? Aurora Borealis. How do you know it's Borealis? How do you know it's not Australis?
It's the northern ones, not
Right. Aurora Australis is the southern lights. Australia basically means the southern continent, I believe. And Aurora Boreal means northern. So that's the northern lights. And I may have spelled Australis there incorrectly. It's not like I write it all the time. But those are southern lights and northern lights. What causes those things? It's got to be something to do with magnetism because that's the topic du jour. That did not erase much. I got rid of the aurora. Let's not worry about that. So we're going to talk about magnetism here. The Earth behaves like a big bar magnet. Now, I should have all my magnets out. I'll have all my magnet demos out on Friday so we can play around and see some magnet stuff. But magnets, we all have a certain understanding of magnets because we played with them as kids, right? I mean, we have magnets that are on our refrigerators, magnets here, magnets there, and they're fun. I bought a book about the history of magnetism thinking it was going to be useful for teaching. Oh, no, it was written by some crank. But there were some interesting things about the history of magnetism. Like ancient Chinese people knew about magnetism and created little games that used it. Compasses, you're very aware of, I'm sure, they were thought to be somewhat magical. And so there was a lot of mysticism involved with magnetism because they thought there was some kind of magic. Now, the story I've been told about magnets, which is of questionable authenticity, is that the first discovery of magnetism goes to a shepherd boy in the region of Magnesia, which somewhere over there, region around Turkey, I think. And he's got a walking stick that's got a metal tip on it. And he notices as he's walking that it sticks to some of these rocks. And so these rocks from Magnesia that the iron would stick to were called magnets. That's the story I was told. And I tell it because it's somewhat interesting, maybe true. So what do we know about magnets? First, we know that there is something here because there is a force. We learned about gravity and gravitational force. Then we learned about electrical force. And there were, unlike gravity, gravity only had one kind of charge. What do we call the charge associated with gravity? The charge associated with gravity.
Gravitation.
We call it mass. Mass is the gravitational charge. It's charge here being the thing that is causing or the force depends on. Then with electricity, instead of having just one type of charge, there were two types of charge. And so we call those electric charges, and we have positive and negative. Now with magnetism, it turns out that there are also two types of charge. And to avoid some kind of confusion between electric charge, I presume, they named them north-seeking and south-seeking. North-seeking and south-seeking because if you take a magnet and you make it so it can freely rotate, it will rotate so one side is pointing north, roughly speaking. And so the one that's pointing north, they call north-seeking. And so when we talk about the poles of a magnet, we have the north pole and the south pole. The north pole is the north-seeking pole. The south one is the south-seeking pole. Now, when I say north-seeking, what does that mean to you?
Like the physical North Pole or sound is?
It's pointing toward the physical North Pole is the exact answer. So north-seeking should be pointing toward the physical North Pole. South-seeking pointing toward the south physical pole. Usually I call it geographic. But then, when people started studying magnetism, just like what was discovered by Franklin, they discovered that opposites attract. So the North Pole will be attracted to a south magnetic pole. The South Pole attracts to a North magnetic pole. North will be repelled from the North Pole. So now we back up the picture. We have a magnet and it has a north-seeking pole that points toward the Earth's north geographic pole. But it's pointing toward the opposite, so what magnetic pole is it pointing toward? The south. So that means the Earth's north geographic pole is its south magnetic pole. Hence, in the picture here, it has south on the north side and north on the south side because the magnets are attracted to opposite poles. Now, with magnets, we're going to have limited magnetic work. Limited, sadly, Nathan was asking questions yesterday. My knowledge is pretty much limited now to this as well because it's all I've dealt with in the last 20 odd years that I've been teaching. We're going to talk about physical magnets and just that they attract and repel. And then we're going to talk about electric charges moving in magnetic fields and the forces with that. So we're actually not going to talk about the force between a magnet and another magnet. But there is a force. If I were to put a physical magnet here, so I'll put a magnet like here, and here's the north side, and here's the south side, it's going to have a torque because the north will be attracted to south, the south will be attracted to north, so it's going to have a torque. It has forces going to make it in opposite directions to make it rotate. And so if I put a magnet in magnetic field, there's going to be a torque to make it align. Now, see those lines, the funky orangish ones? We call those magnetic field lines. We've talked about field lines now, and you have a feel for a force field. A force field, what was the whole purpose of the electric force field, the electric field? What was the purpose of that? I think that's also on the worksheet that I made for you. Nobody remembers? The entire purpose of us having electric fields was to make it easy to calculate the forces on a charge when I put it in there. Similarly, the entire purpose of the magnetic field is to make it easy for us to calculate what the force and torque is going to be on something when we put it in that field. So we have magnetic fields much like we have electric fields. And the rules for magnetic fields are the field lines always come out of north and always go into south. And now I have to introduce something that is weird. Magnetic monopoles are not known to exist. What does mono mean? One. So monopole means one magnetic pole. So that means you don't have no naked north and no naked south. That's naked. They always come together. Anytime you have a north, you're going to have a south with it. That's different from electric charge. You can get electric monopoles. You can have an electron which is just negative, no positive. You can have a proton, just positive, no negative. But you cannot have just north. It always has to have south with it. And so that makes the field lines different than electric field lines. With electric field lines always started a positive charge, ended at a negative charge, or they could start and end at infinity. So the charges went out of positive and into negative, and they could start or end at infinity as well. With magnetic fields, because magnetic fields do not come alone, if they came alone, if we just had a north, it would have the same rules as electric fields. But because they don't come alone, magnetic field lines always lose themselves. So if you look at these magnetic field lines, you see the magnetic field lines come out of the north, they loop around and they go into the south, and then they continue on through the magnet, making a complete loop. So there's a difference. But there are other things that are the same, like what did it mean if we looked at the separation of electric field lines? What did that tell us?
The strength.
It told us the strength of the electric field. The same thing is true for magnetic field lines. So if you look here, as you get out here, the spacing is larger. get closer and it's smaller. So that means the magnetic field is stronger when you're closer to the surface, weaker as you go out. Well, what about in the magnet? What would you say about the spacing there? Are they close together or far apart in the magnet? Close. So what does that tell you about the strength of the magnetic field in the magnet? Must be really strong inside the magnet. So we can read the same type of information from these field lines as we did from electric fields. I just skip over that. And I've already talked about this, except for I didn't talk about this. The symbol for magnetic field is B. Why B? I don't know. I always wanted it to be M. M is used in magnetism, but it's not for magnetic field. It's for another thing. So B is the symbol for magnetic field. It has an arrow over it. By now, you should be super comfortable. That means that it has a direction. It's a vector. The units for magnetic field, units of Teslas. We'll learn in a little bit what a Tesla is, but for now, let's just say it's units of Teslas, named after Nikolai Tesla. There is also, that's the SI unit, the standard unit. There's also the Gauss, which, if I remember correctly, 10,000 Gauss is equal to 1 Tesla. So the Gauss is another unit that's used for magnetic field. It's just a much smaller number. That is, 1 Gauss is much less than 1 Tesla. So those are the units we use. And we'll worry about, like I said, how that relates to the base units, the ampere, the meter, kilogram, the second later. And with the no magnetic monopoles, this is the first thing that any logical person thinks of when their teacher tells them there's no magnetic monopoles. They say, wait a minute, I have a bar magnet. It's clearly marked north and south. If I cut it in half, isn't the north side north and the south side south? I mean, it seems real logical. But the answer is no. If you cut it in half, you're going to have the north side stays north and then the middle is south. Or the south side stays south and the middle is north. You keep cutting it and you will never get to the point where you just have a north or just have a south. So you can't just subdivide. The reason is that the magnetism is at the atomic level. The magnetism has to do with the magnetic moments of the nuclei and the electrons and the orbit of the electrons. It's something that is very quantum physics in nature and has to do with the individual atoms. And by the very meaning of the word atom, the atom means that it's something that you can't split, which I know now we say we split the atom, but it's what it means. You can't subdivide the atom and get just a north. So you can cut as much as you want. You're never going to get a single monopole. Already talked about this. The Earth's magnetic field. The Earth does not have a bar magnet in it. As much as it sounds and looks like it in these pictures, it doesn't. What it does have is what we call a geodynamo. There is conducting material swirling around inside the Earth, creating our magnetic field. And as we understand this process, that means that other things that are rotating probably are going to have magnetic fields as well. And so we measure, and sure enough, the sun has a magnetic field, much stronger. Jupiter has a magnetic field, much stronger. Saturn has a magnetic field. Guess what? It's much stronger than ours. Uranus and Neptune have magnetic fields. The inner planets, not so much. Venus doesn't have a magnetic field at all. Mars and Mercury have maybe some really weak magnetic fields or maybe just frozen in previous magnetism. And so we use that to help us interpret what's going on with those planets. Okay, and I'll end with this question. Which magnetic pole is the Earth's north geographic pole? And now, for your fun and enjoyment, the Earth's magnetic poles have been moving really rapidly in the last 10 or 15 years. the drift was something like, I can't remember what the number was, something like 15 miles per year, and then it's jumped up to something like 55 miles per year in the last 10 or 15 years. So the magnetic north, magnetic south are moving very rapidly. Right now, the magnetic south pole is very close to the actual North Pole, whereas 20 years ago, it was in Canada. And nobody knows exactly what's going on, but we do know that the Earth's magnetic field, just like the sun's, will occasionally flip. So what was north becomes south, and what was south becomes north. The sun does it like every 13 years. 13, yeah. The Earth does it on average about every 200,000 years. So no one alive has ever seen it happen, especially because it's been like a million years since the last time we flipped. So we're way overdue for a flip. And so when something like this is occurring, people start wondering, is it going to change soon? Might we see this within the next couple of generations, see the Earth's magnetic field flip, which would be totally interesting. And if you want to talk about things like evolution and how species might have evolved, the magnetic field shields us from a lot of the cosmic, the sun's solar wind, not the cosmic rays. The sun's solar wind. The sun is blowing off lots of charged particles at us. But the Earth's magnetic field deflects them. The northern and southern lights are caused when there is enough charged particles from the sun coming into the Earth's atmosphere that it causes excitation in the atmosphere and we see the light. So when you see northern lights, you're seeing the interaction between the sun's solar wind and the Earth's atmosphere. But the Earth's magnetic field shields us. So you only have the north and south is where you see those. You don't see them where most people live. If the magnetic field in the Earth were to become very weak for a while the switch occurs, then you'd have a lot more ionizing radiation from the sun coming through all of us, which would then be likely to cause a lot more mutations. So if you believe that evolution is driven by natural processes and mutations, it seems to me likely that you would have a punctuated evolution where when the Earth's magnetic field flips, you would have some dramatic changes that may occur. Like fish with 3 eyes. Yeah.
Or like that was happening, would die on the spot, and we'll have to start all over.
There's some options there too. Anyway, now I believe in creation. I'm just pointing this out because it's something to think about, something that's interesting. All right, have yourselves a great day. I'll see y'all on Friday.
Have something very little.